So the last thing we want to see about CT LTI systems is the eigenfunction property, which is going to be very analogous to the eigenfunction property we saw for discrete time LTI systems. And that is, you put in a complex exponential and you get back out the same complex exponential but modified by a magnitude and phase shift. So we'd like to use this eigenfunction property to compute the output of LTI systems with complex exponential input, and in particular show that the eigenfunction implies that LTI systems cannot add new frequencies to the input function, much like in DT. It's the same story, really. So for DT LTI systems, we saw that complex exponentials were eigenfunctions, and that meant that you put in a complex exponential, you get the same complex exponential out, but with a magnitude and phase shift. So the same property holds for CT LTI systems. Let's take a look at x of t is equal to e to the j omega naught t. That's a complex exponential. It has magnitude 1 and phase omega naught t. Right, so we can plug this in to the convolution formula. Right, we have h of tau and then e to the j omega naught t minus tau d tau. From this we can pull out this e to the j omega naught t, which doesn't depend on tau, so we don't need to worry about it inside the integral. And then we get this quantity over here, integral of h of tau e to the minus j omega tau d tau. So that's just a function of, so this is just a function of h and omega naught. So let's define actually this function. Let's define this function here. H of j omega is just this integral of h of tau e to the minus j omega tau d tau. And then we can write our formula up here, h star e to the j omega naught t is equal to h of j omega naught times e to the j omega naught t. What we'll see later on is that this h of j omega naught t is actually something called the continuous time Fourier transform, and we'll have a whole section on Fourier transforms where we'll get into that. But for now, we're just defining it as a function. It pops out naturally when you consider convolving any LTI system with this complex exponential input. So what have we just shown? We've shown that if you stick in a complex exponential e to the j omega naught t, you just get the same complex exponential multiplied by a constant. So this quantity that we define, this h of j omega function, and why are we calling it h of j omega? It's because actually this is also equal to the Laplace transform, and it's the Laplace transform evaluated at j omega. So we'll see that in the coming weeks. But in any case, this number h of j omega, or this, plugging in omega naught over here, it's a complex value. This h of j omega is a complex function. So it's a complex valued function. So we can put it in magnitude phase form. We can write it as magnitude h of j omega, e to the j, we should write it as e to the j phase of h of j omega. And so if we plug in x equals j omega naught t, what we're saying is we're getting, in the convolution at the output, we're getting the magnitude of h of j omega naught plus times e to the j omega naught t plus the phase of h of j omega naught. So that means what we're doing is doing a magnitude and phase shift on the original complex exponential. So what are we saying? We're saying that LTI systems multiply complex exponentials by a complex valued constant, and this is exactly why we say complex exponentials are eigenfunctions of LTI systems. So this is this shorthand phrase that we used to describe this property of LTI systems, that they just manipulate complex exponentials by multiplying by a constant. So if you have a frequency omega naught in your input signal, that omega naught frequency component, which you can think of as e to the j omega naught t, is just going to get scaled up or down by a complex number. In particular, it means that the LTI system can't somehow output e to the j2 omega naught t or e to the j some other omega t, because it can't create any frequencies that were not present in the original signal. Right? This is the same that we saw for discrete time. And so what we'll see next is that linear combinations of complex exponentials, for example, like cosines and sines, produce linear combinations of complex exponentials at the same frequencies. So again, we cannot create new frequencies from an LTI system. We can only manipulate the frequencies that are already inside the input signal. Okay, so suppose we have h of t, and let's just for simplicity, let's look at it as a real valued signal. So the impulse response is real valued. So let's take the complex conjugate of h. So we take h star of j omega. So we take the convolution. We take the definition of the of h, and we put a star on it. We can pull the star inside the integral. So we get h star, and this minus j omega here becomes a plus j omega t dt. And if you squint at this, since h is real, h star of t equals h of t. So you can see that this is actually just plugging in minus omega for omega, so we get h of minus j omega. So what this shows is that h of j omega is actually, well, it's conjugate symmetric, if you remember conjugate symmetry from oh so many videos ago. And this implies that the magnitude of h of j omega is even and the phase of h of j omega is odd. So these are like two facts which we can pull out of the this conjugate with a G, conjugate symmetric. So as an exercise for yourself, look at the dt version of this story where we had h of e to the j omega, and why don't you try showing that that is also conjugate symmetric with even magnitude and odd phase. Going through that exercise will make you kind of understand this argument a bit better. Okay, let's do an example. So suppose h of t is e to the minus 3t u of t. We had a familiar decaying exponential impulse response. Then we can just plug it into, we want to know what h of j omega is, so we can just plug it in to the formula. So you get e to the minus 3t, e to the minus j omega t u of t. This u of t is going to make the lower limit of this integral 0. And then we get e to the minus 3 plus j omega t from 0 to infinity. So we're just going to get, in fact, 1 over 3 plus j omega. And now we use multiply top and bottom by 3 minus j omega, and we can write it in Cartesian form as 3 over 9 plus omega squared minus j omega over 9 plus omega squared. Or if we want to write it in magnitude phase form, we can write the magnitude is going to be 3 squared plus omega squared over 9 plus omega squared. So 3 squared plus omega squared over 9 plus omega squared squared. And this is going to be equal to 1 over 9 plus omega squared. So that's the magnitude. And then the phase is going to be minus j omega over 9 plus omega squared over 3. So we get this omega over 3, and the minus sign comes from this minus sign here. So this is input e to the j omega naught t gets a gain of 1 over 9 plus omega naught squared, which is, I guess, more of an attenuation probably, and a phase shift of minus 10 inverse of omega naught over 3. Okay, so let's now try it with an input signal that's a cosine. So let's say look at cosine 6 pi t. So first step, you see a cosine. One of the first steps you might think of is to Eulerize it. So we Eulerize it here, splitting into a half e to the j 6 pi t plus a half e to the minus j 6 pi t. So now we're going to convolve the output. So because the convolution is a linear operation, if we're convolving x with h, it's the same as convolving the first term with h and the second term with h. And the first term has a frequency omega naught of plus 6 pi, and the second one has minus 6 pi. So we can plug into our formula that we had from the previous slide. We can see that we're going to get this half is going to come down, and then we're going to have 1 over 9 plus 36 pi squared, because that's omega squared, e to the j 6 pi t, and the phase shift, which is minus j tan inverse of 3 over omega, which is 1 over 2 pi. And similarly, we get on on the second term here, this one, we're going to get a half 1 over 9 plus 36 pi squared, because minus 6 pi squared is also 36 pi squared. And then we're going to get minus j 6 pi t, and we're going to have minus j tan inverse minus 1 over 2 pi. And why is that? Because this thing is omega over 3. Again, when omega is now minus omega naught over 3, and this omega naught is minus 6 pi. Minus 6 pi over 3. So we're going to get minus 1 over 2 pi. And this is great, actually, because these minus signs are going to cancel out for us. And we can write this as the total gain 1 over 9 plus 36 pi squared times a half. Now gathering the terms, we just gather the j's together. We get 6 pi t minus tan inverse of 1 over 2 pi. And then over here, we're going to get minus j times 6 pi t minus tan inverse 1 over 2 pi. So in the end, we get 1 over 9 plus 36 pi squared cosine 6 pi t minus tan inverse of 1 over 2 pi. That was a lot of algebra just to do one example, so let's see if we can do things more generally. So suppose we have h of t, and x of t is cosine omega t. Then y of t is equal to h of j omega. We Eulerize, so this is Eulerizing. Then we write h of j omega in magnitude phase form. So we get 1/2 e to the j omega naught t plus h of j omega, phase of h of j omega, and h of minus j omega, 1/2 e to the minus j omega t plus phase of h of minus j omega. Then we use the fact that magnitude is even, phase is odd, to write this as this term stays the same, but this term, h of minus j omega, is actually, the magnitude is the same as h of j omega because it's even, and we flip signs over here because the phase is odd. So now we can Eulerize or de-Eulerize, however you want to think of it. We have the magnitude, and we have, back to our cosine, we have a cosine now with a phase shift of h of j omega. So this is called the sinusoidal response of the system. We don't really need these parentheses here. We put in a cosine of omega t, and we get back out the same cosine of omega t, and we get the same cosine with a magnitude shift and a magnitude gain and a phase shift. So that's the same as we saw for discrete time as well. And if you want to see another example, kind of walk through this derivation again yourself to learn a bit more, try doing the whole thing with sine omega t. Okay, so it might be good to try these sort of things yourself. So try these couple of examples here, and they're sort of different complexity, and being able to find the sinusoidal response to these input sinusoids with these different impulse responses will give you a sense of how this sinusoidal response thing sort of really works.